In this video, we'll look at the ADALM2000, also known as M2K, and its digital pins, and the I/O instrument that is the simplest way to use them. After that, we'll blink some LEDs using the M2K's pattern generator. A digital I/O pin is one that is in one of two states. It's either high or low. The M2K's pins can be configured to be either inputs, which read if a signal connected to them is high or low, or as an output, where they're either set to high or low, and high is 3.3 volts and low is something near zero. The pins are 5-volt tolerant, which means it's okay to connect to 5-volt logic. The 5 volts won't fry the 3.3 volt input. It's also 1.8 volt compatible, meaning that a 1.8 volt logic high should read as a high. So you could use the logic analyzer, for example, to evaluate a 1.8 volt circuit. And finally, the output can be set to either push-pull or open drain. The latter is an advanced topic that I won't go into in any detail, but it basically means that the high state comes from a pull-up, and multiple sources could pull the signal to be low. For example, I2C might use that. Here's a good question. When a digital I/O pin is configured to be an output, how much current can it provide? For example, is it safe to drive a bright LED directly? That might take 20 milliamps or more. Is it okay? This can be a complicated topic, and unfortunately, I don't find a simple answer in the M2K documents. But there is a clue that you can see in the M2K schematic. Each digital I/O pin has a 220 ohm PTC thermistor in series. This is a protection device. It's essentially a resistor whose resistance goes up as the thermistor heats up, and that reduces the current. So anyway, that 220 ohm thermistor, even at room temperature, is acting at least as a 220 ohm resistor. So if you were to have a 330 ohm load attached to a digital I/O pin, then there would be a voltage divider, and you would measure something like 1.98 volts across the 330 ohm resistor. Do we see this? Here's the circuit that we can use as a test. Essentially, we just have actually a 328 ohm resistor connected to digital output D0, and we'll measure that using the 1 plus pin and the built-in M2K voltmeter. And we'll also have the D1 pin connected directly to ground, and we'll measure it with the 2 plus pin. And then we can see whether the voltage drop happens. Sure enough, the voltmeter's channel 1 reads a little over 1.9 volts. So that PTC thermistor is definitely there. And we also see on voltmeter channel 2 that a I/O with no load at all is having a voltage level of a little more than 3.2. That's consistent enough with 3.3. I'll just mention my M2K's voltmeter isn't totally accurate. My real voltmeter measures that as 3.3, but it's close enough. So what's the conclusion? My opinion is that the presence of that thermistor suggests that the M2K is not designed to drive large loads. It's intended to drive high impedance loads, meaning not put out too many milliamps. The 330 ohm resistor test, that represented driving 6 milliamps, and it worked, but it's a little bit more than makes me comfortable. So onward to blinking some LEDs. My LEDs are very old and unusual. They have integrated resistors, and that's why you won't see any current limiting resistors on my connection diagram. I measure that they draw 3 milliamps from the M2K. That's a lot more comfortable, but still, I might go for even less than that for anything I'm going to run for a long time. I would not push the M2K's outputs without better information. So if you decide to blink some LEDs from an M2K, I'd suggest using at least a 1K current limiting resistor. Here are the connections that I'm going to use to blink my LEDs. I'm going to use 4 of my LEDs that have internal current limiting resistors. And I'm going to connect them to digital I/O pins 0, 1, 2, and 3. Those will be the pins that are configured as outputs. I'm also going to connect them to digital I/O pins 8, 9, 10, and 11. Those will be configured as inputs so that the M2K can read what it's outputting on the output pins. In addition, I'm going to connect the analog input pins 1 plus and 2 plus to my third and fourth LEDs, so we can look at them on the oscilloscope going forward. So there are lots of YouTube videos that blink LEDs. I guess we're adding one more. The first thing we can do is look at the digital I/O instrument. It's really quite simple and even limited in what it does. So first of all, you can pick whether given pins are inputs or outputs. So we'll make the first two outputs and then click run. And now by clicking here, I can set their value. So I can see I can turn my LEDs on and off. And and when I do that, the other two pins that are connected, so zero's connected to 8 and one's connected to 9. So when I change the output of one, the output is red on 9 and shows up like this. It doesn't happen very quickly though. So if you have quickly changing signals, you might not see these things blink. But that's pretty much all there is to the digital I/O instrument. Next, we can look at the pattern generator. What it does is outputs patterns like a just a clock or something like that onto the various pins. So the first thing you do is you go to this menu here and you can pick which pins the pattern generator will use. And so let's just pick one of them to start with. And then if you double click on it, you can tell it what to do. So you can pick a frequency. It's currently set to 1 hertz. Let's make it 2 hertz. And pattern is clock. You have your choice of all of these things, but we'll stick with a clock pattern to start with. And you can give it a phase and a duty cycle. Let's just make it 50%. And then if I run, we ought to see an LED blink, and we do. So LED 1 is blinking. So what else can we do with this? Let's see. Let's stop it and go back to here, and let's put 4 pins into for use by the pattern generator. And then if you click group, you can group them together to serve a purpose. So you have to select them. So if I can do this right, this is sometimes a little tricky. So now all 4 are selected, and with any luck, that puts all 4 into the same group. Yes, it looks like it did. And now we can pick what's going to happen with these. Like if I run this, I think they'll all just blink together. Yep, because it's set to clock. And but let's pick something more interesting, like binary counter. And 5 kilohertz is way too fast. So let's change that to hertz. And maybe we'll just do 2 hertz again. 2 hertz. And run. And we should see a binary counting pattern. And it looks like we do. So, that's kind of the wonders of the pattern generator. It is able to generate clocks up to, well, what is the maximum frequency it will allow here? It just keeps going. Yeah, 50 megahertz. So those are supposedly counting very quickly now. I don't know how usable speeds this high really are, but yeah, it's capable of pretty high speeds. So that's the pattern generator in a nutshell. Let's use the oscilloscope to look at the output of these digital signals driven by the pattern generator. That could be fun. But first, let's increase their frequency to something a little bit more interesting. Let's go up to, say, 25 kilohertz and go to the oscilloscope. And let's adjust our horizontal time base. Let's see, to try to see the signal a little bit better. And there it is. Maybe here is good. And it's jumping around a bit. And I think the reason for that is that it's triggering on channel 1, which by the way is connected to D2, and channel 2 is connected to D3. So these are the signals coming from the pattern generator that are at the slowest frequencies. Channel 1 is D2, so that's 1/8 of the pattern generator clock, and channel 2 is then 1/16 of the pattern generator clock, and that looks right according to the oscilloscope's measurements. But anyway, we can fix this jittery display by triggering on channel 2, because right now it's randomly triggering it's triggering on channel 1, and that's capturing either the rising edge or the falling edge of channel 2. So by triggering on the slower channel, it should clean it up, and it does so nicely. And so that's a pretty good looking signal at 25 megahertz pattern generator clock. So let's crank it up. Let's go all the way. I think the fastest it can do is 50 megahertz. So go back to the oscilloscope, and I think we need to adjust our time base. a lot. Yes, and so here we are. That's actually looking pretty good for fairly fast signals. So again, one eighth of the clock, so 6.250 megahertz on the channel one, and then 3.125 megahertz on channel two. That's actually looking pretty good for fairly high speed signals. Let's go back to the pattern generator and maybe pick 50 megahertz or 25 megahertz, I mean to say. And yeah, pretty good. And the rising and falling edges are pretty well aligned, and the scope's doing a good job of showing it. So at these speeds, it's pretty impressive. So that's a look at the pattern generator and the oscilloscope viewing the pattern generator. We'll end here. Thanks for watching. In a future video, I'll look at the logic analyzer.